1 second. It is, yes, now you may start.
Okay. So welcome to the last but one lecture, fourth lecture in the mini course series. So today the plan is to cover groups of type F4, E6 and E7 with the remark that only groups of type F4, we as of now we know only groups of type F4, all the twisted forms are known and how to construct those. But the other types, I will just show you how to construct the simply connected groups of split type, and other types one doesn't know complete classification. Whatever little is known, I may try to cover it in the last lecture. Let's see, which is the next lecture, of course. So for today, let me start with the basic objects which we will need. So we again assume base field has characteristic different from 2 and 3 for simplicity of notation and calculations. And suppose C is a composition algebra over the field, and gamma is a diagonal matrix in GL3 of K. Then you look at the 3 by 3 matrices with entries in the composition algebra we fixed. On that, we can define an involution which maps a matrix X to gamma inverse X bar transpose gamma. So this is clearly an involution. We just take fixed points of this involution in the algebra M3C, and that we denote by H3C comma gamma. So that is all X such that X star is X. On this, there is a product one can define, sort of complement of the Lie bracket, which is if X dot Y denotes the matrix product, then I define XY to be half of X dot Y plus Y dot X. So this one can easily see, this is certainly a commutative, and easily check this is a in fact, not at all associative algebra. As long as, so we are, all versions of C will result in non-associative algebras. So this gives us a K-algebra structure on this vector space, and dimension of this vector space is 3 plus 3 times dimension of C. I did not show you the form of matrices here today. When I come to that, I will bring that last lecture slide perhaps, where it is clear that on the diagonal you have scalars. So that gives you this 3 dimension, and off diagonal entries are from arbitrary entries from the composition algebra C. That gives you 3 times dimension C. So that's the dimension of this algebra. Some basic properties of the product here are the following. There is some weak associativity that one can have here. Namely, so first of all, it's power associative in the sense I can just write x power n without worrying about the order of taking the products. Then x square times yx is same as x square y times x for all xy in the algebra. And the identity element for this product is the usual identity matrix. By the way, I must apologize to you all today. Particularly, I found lots of mistakes in the notes and omissions also. So I will try to make remark about those when I come to those, and hopefully one day I can correct these and type them out. But let's see. So the second basic feature is the trace map, which is defined as usual, the sum of the 3 diagonal entries. So it's a linear form on the algebra. That gives rise to the bilinear form, which I denote by angular bracket xy. That is trace of x times y. So this is the bilinear form, which in turn gives a quadratic form, which is this qx defined to be half of trace x square. So this is a non-degenerate quadratic form on the algebra. These are some properties which I am not going to prove. I'm just listing them. So this is a very important object for us, this quadratic form and the bilinear form. We will work with these. So trace of x in this language is just the bilinear form evaluated at x and e. And here again, we have a characteristic equation for every element in this algebra. This is the usual 3 by 3 matrix Cayley-Hamilton equation. So this is x cube minus trace of x times x square. And here I have though written minus, you can convert it into a plus by switching these two guys here. And then you see this is half of trace x square and this is half of trace x squares, which is the usual entry in the 3 by 3 matrix case. And the last constant we call the determinant of x, which is indeed the usual determinant, but taken carefully, calculated carefully, because we are no more in possibly in a non-associative coefficient algebra. So this should be computed carefully. So this, of course, is going to be a cubic form on this algebra because of course, it's not immediately evident from writing it like this, but when you expand it out, you see that it will be a cubic form. If you list all the entries, all the variables. So there are dimension of composition algebra, many dimensions, 3 times those and plus 3. So these many variables, you get a cubic form, which is sort of expected because usual matrices also determinant is a cubic form. So any questions so far? We will use these ideas freely as I proceed. So please don't hesitate in stopping me anytime. Shripad, I request you to intervene once in a while to let me know things are going fine. Otherwise, it should not repeat what happened last time.
Sure, no problem.
Okay, so the fourth property is that this is immediate from this equation that x is invertible in the usual sense if and only if the determinant of x is non-zero, because you can factorize x out here and take the determinant on the other side. So that shows this property. Fifth property, very important. I have just listed it casually, but it's a result one needs to prove that any automorphism of this algebra preserves the trace linear form, therefore the quadratic form as well as the cubic form determinant. So automorphisms they give isometries of all these three forms. One is linear, other is quadratic, and then the cubic. And this bilinear form, trace bilinear form, is associative. This is the terminology used in Lie theory, which means that product of xy with z, the angular bracket of xy with z is x comma yz for all xyz. We will need this. This is not such a difficult thing to prove, and we will use this later. So I just list it here. So these are the 6 properties I have listed here. There are many more, of course. And now let's put one notation here. When the involution matrix gamma is identity matrix, one just writes H3C. Though I'm not really going to use this notation in this, I'm just telling you here. I thought I will use it, but I forgot to use it. So the remark here about these algebras, one more interesting remark is, if I take composition algebra of dimension 1, 2, or 4, which means the base field, or quadratic étale algebra, meaning composition algebra, of course, with the norm, or a quaternion algebra, then this is actually an associative algebra. M3C is an associative algebra, and star is an involution on that in the usual sense. And one knows that this involution is either orthogonal involution, unitary involution, or symplectic involution. So as these dimensions change, you have these possibilities. And when you compute the automorphism group of this algebra, then as an algebraic group, you will get classical groups here. So either they are orthogonal, unitary, or symplectic group. You may have to take connected component here in some cases. So the interesting case occurs when we choose octonionic entries. So that is the case which will result in this big group F4. So the next section here is Albert algebras, what are called Albert algebras, named after Adrian Albert. Uh, let's start with the split octonian algebra over K, and then construct this algebra that I mentioned. So once you take C split, one can show that this involution matrix can be absorbed in the splitness properties and it goes away completely. So you can just assume as well that this is the identity matrix. And then we call this algebra as the split Albert algebra. We will see soon that automorphisms of the split Albert algebra gives you the split form of F4 over K. And in general, we can define an Albert algebra over K to be a K algebra, which is a twisted form of this split Albert algebra. So over some field extension, it becomes isomorphic to the split Albert algebra over that extension.
Manish, I have a question.
Yes, yes.
Just for the sake of asking question, actually.
Yeah, sure.
Make sure that we are.
Yes, no, please do that.
So even if C is not split,
yeah,
and if we have gamma to be the identity matrix,
yeah,
then do we get the split Albert algebra?
No. This is the only case when you get split. So when the Albert algebra by definition is split, when the coefficient algebra is split, and in that case, it is this. With you can forget gamma and just write identity there. They are isomorphic, and in no other situation you will get split Albert algebra. C has to be split for that.
Okay, thank you.
Does that answer your question?
Yes.
Okay. Indeed, you please ask me, however, basic questions so that I know things are going fine. So one has a name for algebras which are of this form, where we allow arbitrary octonians now. Any such algebra is called a reduced Albert algebra in this terminology, which is really silly in the commutative algebra sense, because we are not discussing nilpotents here to call it reducer or anything. This is just some old terminology, which is same as saying it has zero divisors, or again, which is same as saying the norm or the determinant has non-trivial zero. So these are the three equivalent properties which characterize such algebras, H3C gamma. Okay, so remember here I am just defining a general notion of Albert algebra as those which become like H3C gamma over some extension. So these may be possibly division algebras, okay? But using some basic descent theory, one can prove that these properties that I listed, 1 to 6, of course with some slight obvious modifications, they all hold for any Albert algebra. For example, the first property as it is makes sense for any Albert algebra. Here, of course, identity will not look like this anymore, possibly. Then linear functional, there is a linear form which is called the trace form. Over some extension, it coincides with this usual trace. Similarly, there is a quadratic form that will give rise to, and then there is a cubic form and so on, which are all the same objects but over a field extension now. So, and then every element satisfies such a cubic polynomial. So these are the features of these algebras, some of the important features. And I just mentioned here that by descent, one can show that these kind of properties hold for any Albert algebra over K. Even in that division, algebras are included. So one knows there are only two kinds of Albert algebras, either they are division or they are of this form, H3C gamma. There is no other third possibility. So these are all. So, and one knows now how to construct all of these. So therefore, once we prove the final result, it will be clear how to construct all forms of F4. So remember now of course, so we have the candidate algebra now, and which is just dimension 27, and which is less than the dimension of split F4, which is 52. So it's a welcome progress. We have a smaller algebra than the Lie algebra in the size of sense of dimension. and whose automorphisms we are aiming to prove will give us groups of type F4. So the first task is to pin down a variety which is irreducible on which the group acts transitively, going by what we did in the earlier case of G2. So what we do here is, let's fix a reduced Albert algebra. Soon we will be working over the algebraic closure, so it will be automatically split there. But anyway, at the moment, let's just start with any reduced Albert algebra. We call an element to be idempotent if, as usual, u square is u. And there is a special class of idempotents called absolutely primitive. So this means you cannot decompose u as a plus b, where a square and b, a and b are idempotents, and their product is 0. And this property should hold over arbitrary scalar extensions of the base field. So that is the meaning of absolutely. So this property should hold over all extensions. Then you call the idempotent as primitive. And one can easily show that this is equivalent to saying trace of this idempotent is 1. Or the quadratic form Q evaluated at this is half. So these are all equivalent properties. So we will look at the set of all such idempotents and see soon that that's a variety. And here is a property that I could have proved, but I am refraining from proving this here. If K is algebraically closed, then the automorphism group acts transitively on the set of all these kind of idempotents. So given any two primitive idempotents, there is an automorphism mapping one to the other. So this property I'm going to assume it's not difficult to prove. I will give you an indication of the proof when I come to that little later. So at the moment, let's just remember that an idempotent is primitive if its Q value is half or the trace is 1. And remember the diagonal matrices in H3C gamma have scalar entries. So we have the usual matrix idempotents there, 1, 0, 0, 0, 1, 0, 0, 0, 1. So those are examples of primitive idempotents. Okay. So while we have the potential candidate here, namely the set of all primitive idempotents, because the group acts transitively on that, but we don't know yet whether it's a variety. Of course, the set of all idempotents is a variety, and even primitive idempotents will form a variety because I know the equation Q u equal to half that cuts down the variety of all idempotents into yield the variety of primitive ones. And what we want to know is compute the size of that variety, compute isotropy at an element, and so on. So that's the next step. We want to compute the isotropic group at a primitive idempotent. So any questions so far in chat box or otherwise?
No, there are no questions in the chat box.
Okay. So let's fix a primitive idempotent U. And let's look at the two-dimensional space spanned by them, the identity element and U. They span a two-dimensional subspace. And let's take the perp of that with respect to the trace bilinear form. So that is precisely all x in the algebra H3C gamma, which I am calling as A, which have trace 0 and which are orthogonal to the primitive idempotent U. So this is the space I'm going to work with. It's immediate calculation that this quadratic form, when you restrict to E, remember E has dimension 25 because this is 1, so 2 dimension, and then total dimension here is 27. So E is a 25 dimensional vector subspace and Q is non-degenerate on that. And as I said, Q value at U is half or trace is 1, either way you like it. Now let's look at this. For any x in E, So I told you that associativity property of this bilinear form, we will use that now. Let's look at ux. I claim that ux again belongs to E. Why is that? So I must check it is orthogonal to E as well as orthogonal to U. So this is orthogonal to E because this form is same as U and this x goes to this position to give me ux, and that is 0 because x was in E. Similarly, with U, I can write this as ux and equal to xu. So I can write this as xu and put u here. So that again gives me x bracket u, which is 0. So this shows that left multiplication by u maps E to E. So that map I am denoting by t. So t is nothing but x goes to u times x from A to A, and we know it maps E to E. This is what we checked here. And also, you see tx is just ux. So once you write ux as xu, it goes again here to give you that tx comma y is same as x comma ty for all xy in u. So this is in a way this says that t is a symmetric operator. It coincides with its own what is called I don't know, adjoint or something with respect to the bilinear form, right? So we have this property t is symmetric and t stabilizes E. Now here is a shocking equation. One would expect that u being an idempotent, the left multiplication by u should satisfy t square equal to t. But that is not true because this object is no more associative. Instead, one has this equation, t square is half of t. So this is something I realized with a lot of struggle later. When I was learning these things, this is really strange. So you have therefore possibilities for eigenvalues as 0 and half. And then accordingly, you have these eigenspaces, EI, so which is all x in E such that ux is 0 and all x in E such that ux is half of x. So these are the 0 and half eigenspaces for the operator T. We will compute their dimension in a spatial situation. So before I do that, I will just introduce notation. For the Albert algebra, I denote by A12 these matrices which have 1/2 or 2/1 position something filled up, otherwise 0. Similarly, I have A23 and A13 or 3/1. They are same. So this is first row, third column. There is something, and otherwise 0. So these are the definitions of these 8-dimensional subspaces. These are all 8-dimensional. I am working with octonionic entries. Remember. Now, I'm sorry that here there's a goof up. What I want to say here is, let's take the standard idempotent u equal to u1. So it is 1, 0, 0. I take u to be 1, 0, 0, u2 to be 0, 1, 0, and u3 to be 0, 0, 1. I'm just trying to write down these E0 and E1 in the case of U equal to U1. It is just E0 is just this space. So you have 0, 0 in the first row, then so this is 9-dimensional space, which is these octonionic positions and alpha minus alpha here. Alpha runs over all scalars. So this is a 9-dimensional space. And E1 is this 16-dimensional space, A12 direct sum A13. So these are explicit checkings. I'm skipping those calculations. One can check that these are the eigenspaces, okay? For the standard first idempotent. And once you do it for that idempotent, you're done for all primitive idempotents because of transitivity. So that was the idea, to compute dimensions of E0 and E1. We can assume we are in the standard position, and there these are direct calculations. So I have these explicit dimensions now. Dimension of E1, which is the half eigenspace for operator T, that is 16, and the 0 eigenspace has dimension 9. So let's denote by G bar the full automorphism group of A. and capital K is the algebraic closure, fixing one algebraic closure for K. And G bar U denotes the isotropy at U. That means those automorphisms of the algebra which fix U. Now, if you pick any such automorphism, if it fixes U, of course it fixes identity element also. Therefore, it will fix this two-dimensional space completely. And right at the beginning, I said that automorphisms preserve the trace and the trace bilinear form. So it will map this orthogonal complement to itself. Therefore, this this G bar U will map E to E. And once it maps E to E, next is zero. Of course, zero space will go to itself and half space will go to itself. This notation is bad. I should have called it E half maybe. So these are stabilized by any automorphism belonging to the isotropy at U. So we have these two representations for this group. Okay. A little bit noise about basics on, I don't want to say this too much in detail, but quickly, Clifford algebra is just tensor algebra modded out by the two-sided ideal generated by such elements. So you basically want a relation that square of a vector should be the q value at that vector. So that is the relation Clifford algebra should satisfy, and some universal property with respect to that property. And let's denote if this is the projection map. So this is the quotient of TV with I. Pi denote the projection map TV to CVQ. And let me denote V image of V tensor W under this projection as V dot W, V times W. Then, if E1, E2, En is a basis for V, then one knows that the products EI1 up to EIR, where I can order I1 up to IR in this increasing fashion, they all form a basis for the Clifford algebra. And as a result, Clifford algebra, I did not write down, which I need actually. Dimension of the Clifford algebra, therefore, is 2 power n. So you just choose a subset of indices and that gives you a basis vector. So that gives me, together with 1, by the way, I have to add 1 also. So that corresponds to the empty set or subset of the indices. So I have 2 power n as the dimension of the Clifford algebra. And one knows some properties of this. This is a central simple algebra if n is even. Please correct me if I goofed up somewhere here. What I need really is when it is odd. So let me define quickly what is the even Clifford algebra. So I told you Clifford algebra is generated by products of vectors. So it has a subalgebra generated by even products of vectors. So if you take evenly many vectors in V, take their product and take all such products, even many products, and generate a subalgebra. That is called the even Clifford algebra. Okay. And then one talks about what is called the even Clifford group. The Clifford group, which by definition is all elements which are units in the Clifford algebra, and they normalize V. So this is all T in CVQ cross, which with TV T inverse equal to V. And even Clifford group by definition is the even part of the Clifford group. Those are precisely these kind of elements. These are precisely even a product of even many vectors such that Q of those vectors is not zero. This forms a subgroup of the group of units. This is called the even Clifford group. And then spin group is by definition, just take the product of these Q values, that should be 1. That gives you the spin group. Okay. And this is an algebraic group, and this is the simply connected cover of the special orthogonal group. Why do I need this? I need it because I want to describe to you this group. What is this group? So of course I could assume all this, but it doesn't harm to recall quickly. Shripad, I'm audible, I hope.
Yes, yes.
So let's go back to the task at hand. Remember E naught for the fixed idempotent U equal to the first 1 and 0, 0, that idempotent. We know that E naught looks like this: octonionic position and one scalar position here, really alpha minus alpha. So that's a 9-dimensional space. And if you calculate the quadratic form on X, value at X is looks like this: alpha square plus gamma 3 inverse gamma 2 octonionic norm of C1. So this is a 9-dimensional non-degenerate quadratic form. And the point I am trying to make is isotropy at that first idempotent U, which I am calling it U, is isomorphic to spin of this 9-dimensional quadratic form, spin group of this 9-dimensional. Very explicit calculation, which I told you how this works and so on. So that representation actually gives you an isomorphism here. And because the automorphism group acts transitively, this will hold for arbitrary primitive idempotent. So you start with any primitive idempotent, then you have this isomorphism, that isotropy group in the sense of subgroup of the automorphism group is actually isomorphic to spin group of a 9-dimensional quadratic form, which is really coming from the trace quadratic form restricted to a 9-dimensional space. So this calculation we have, and the dimension of such a group we know. 9-dimensional spin group has same dimension as SO9, which is 9 into 8 by 2. So it's 36. So we can now start computing dimensions. So any questions so far? I hope I'm not going too fast.
None so far.
Okay. Are there participants today? Sorry, I just joke. Silly joke. Yeah.
Right.
Yeah. So the set of, as I said, the set of idempotents in AK is a variety. I'm looking at algebraic closure, over the algebraic closure. It's a variety, and elements which are primitive satisfy this condition. So it's a sub-variety, which is what we are working with. I'll call that variety of primitive idempotents as V. I have forgotten. I have written here V. I think here also I had forgotten, and then at the last minute I inserted a V there. So let's start with a primitive idempotent. There are some ugly facts here which I am just quickly going to say. And pick any x0 in E0. So that means, remember, E0 is all the guys which are killed by U. So U times x0 will be 0. So pick anything here with Q value 1 over 4. That's possible because of, see this explicit expression. You can just take alpha equal to half and C equal to 0. So that will give you one such element. So any element, so there's a lot of flexibility here. Pick any element and then construct. So U1 is the idempotent you start with, and call U2 as half of E minus U plus x0, U3 as half of E minus U minus x0. Then one checks straightforward calculation again that all these are idempotents. Their sum is equal to identity, and also it will follow that they are primitive. So these are primitive orthogonal idempotents, and their sum is equal to the identity element. And one knows that you cannot go more than 3 in this theory. You can only have, because of that equation we saw, that's a cubic equation. Somewhere that implies that you cannot write an idempotent in the sum of more than 3 idempotents. So in any case, we have this equation. Now, so V is a variety. In that, let's define a Zariski open subset. Let's define 3 Zariski open subsets, V1, V2, V3. The definition of Vi is those idempotents belonging to V which are not orthogonal to Ui. So those which are orthogonal to ui will form a hyperplane. I am looking at the complement of that. So vi is those idempotents living in V which are not orthogonal to ui. So V1, one can check by some ugly calculations, can be parameterized as follows. So I am looking at the first one. It consists of elements T which look like this. They are some explicit expression parameterized by elements of E1 actually. So it looks like Qy plus 1 inverse multiplied to U plus half Qy into E minus U plus again some function of y which is written here plus y. So this gives you an isomorphism of V1 with an open subset of E1. Remember, E1 is an affine space. It's a vector subspace. So I am giving you an isomorphism of V1 with an open subset of E1, and that open subset is given by Qy not equal to -1. And the isomorphism is just map a T to this Y. Any T here looks like this. So this is explicit calculation. So you mapping it to Y gives you an isomorphism. So in other words, we showed therefore V1 is irreducible. So V1 is irreducible and the dimension is same as dimension of E1. So dimension of V1 is 16 and it's an irreducible variety. And similarly for V2 and V3. So you have three, so this finishes this part of my, half of the lecture is done. So any questions so far? I will continue with this. So I'm looking at trying to prove that the variety of primitive idempotents is irreducible and we will compute its dimension. And the dimension, of course, we already have it here.
This is the variety on which the group will act and then we will prove it is connected.
Yes, exactly. Okay, so let me diminish this and hope the next one is visible now. Is it visible, Shripal?
Yes, it is.
Okay, so similarly, V2 and V3 are irreducible of 16 dimension. And then I am skipping details now. One can show that V1, so of course, I have to write here, V is also equal to V1 union V2 union V3. So all these three open subsets cover V and their intersection is irreducible in each of the Vi. So this all can be shown explicitly. So that proves by simple arguments that V itself is irreducible and has dimension 16. So this is just basic geometry going on here. So you take the closure and so it contains Vi for all I and they cover. So that means this has to be equal to V. So V is irreducible of dimension 16. Okay, so basically the only thing to take away from here is V is the variety of primitive idempotent. So that you can, now you go home and if you want to do it yourself, you can do it. You have the information what all means and so on. So the dimension is 16. Now the next, so the main result here is that this group G bar is connected simple defined over K of type F4. So this I have not given a proof of so far. I will indicate later when we go to E6 how that is proved, but I am not going to do details again. So G bar acts transitively on the irreducible variety V we showed just now, and we calculated the isotropy to be spin 9. 9 is just to indicate 9 dimensions. So that tells me that dimension of G bar is 16 plus 36. So that is 52. So we got the dimension here. And again, we see G bar is connected because V is irreducible and isotropy is connected. So G bar is connected. Next is to pin down the type. So how do we do that? So let's take the trace zero elements. So that is a 26 dimensional space. And so here I have written for a fixed primitive idempotent U, it breaks down as the one dimensional space, which is multiples of E minus 3U plus E0 and E1. Remember, these together form 25 dimensions. and the remaining one dimension in E perp is this. So this is easily computed. And because elements of the automorphism group fix identity element and preserve the trace form, it maps W, which is what I'm calling as E perp. It maps W to itself. So the important lemma for reductivity of the group is to prove W is faithful and irreducible. So that's what I'm doing. So why is it irreducible? What we will do is we will use the isotropy at U. We showed that this isotropy, of course, leaves this fixed pointwise. This leaves E0 invariant and E1 stable. Both E0 and E1 are mapped to themselves by G bar U. And it's also, one can see that the action on E0 is via rotations. So, which means determinant 1 orthogonal transformations. And because of that, it follows that E0 is irreducible for this. So that is what is called a vector representation or something, right? So this is irreducible for the spin group. And this other one is 16 dimensional. So if you take the even Clifford algebra, on which this is sometimes called the spin representation of the group. It's on the even Clifford algebra, which is 2 power 4 dimensional. Am I making sense, Shripad? What am I saying? 2 power 4. Yeah, so 9 is.
Can you please repeat what you were discussing?
Yeah, 1 second. So Clifford algebra, I'm saying that this representation can be shown. I mean, GU is of course acting on E1. I am saying that this can be shown to be equivalent to the spin representation of this. And that is half. Anyway, let's forget this. So I'm just saying this is the spin representation. So whatever that is, I am not defined. I'm just trying to tell what is the spin representation. So let's forget it. It is known that this representation is irreducible. Okay. So it is coming from the even Clifford algebra. That's all I wanted to say. So that shows that W, which is here written down here, it is sum of 3 irreducible representations for the spin group on 9 of a 9-dimensional quadratic form. These are all irreducible, and this is 1, this is 9, this is 16 dimensional. Okay, this is what it is, and G, that spin group is subgroup here. And what we know now, so here I had fixed an idempotent and I wrote this equation. Now I can change this idempotent. So the argument is that, so now we know this acts transitively on V. So if I had an invariant subspace of W, it will also, so I can choose, so suppose, let me call that invariant subspace as Z. Suppose Z is an invariant subspace of W with respect to G bar action. Now I will restrict that to GU and say that there must be an irreducible such contained in that Z for GU action. But I know that G bar acts transitively, so that any non-trivial element there can be pushed to some other invariant part. So this will not be irreducible therefore. So one can show using transitivity, I am just not saying it nicely, that W is actually irreducible for G bar. Is this clear, Shripad? Should I explain this more? So
I think I will let others take a call on this.
Yeah. So the point here is the following. I wrote for a fixed primitive idempotent the trace zero elements as direct sum of 3 irreducible representations for G bar U. And now I am saying if W has an invariant subspace, say Z, for the action of G bar, then that invariant subspace will continue to be invariant also for G bar U. and therefore there will be an irreducible subspace of in that for G bar U. So you may assume G bar that Z itself is irreducible and get a contradiction. So contradiction will follow from here. So that is irreducible means it has to be one of these types. And then you can permute these by the action of G bar. So the invariance will fail there. So because given any two idempotents, primitive idempotents, I have an automorphism mapping one to the other. And that will shift these guys. So this will go to something else, then anything here will go to something else, anything here will go to something else. So that invariant subspace will be disturbed by any such automorphism. So please convince yourself, allow me to continue. I'm just saying that by that transitivity, it will follow that W is irreducible for the group G bar, and it's obviously faithful. So by that lemma, which I called a funny lemma, it follows that G bar is reductive. So this is the whole point. I just wanted to show this. So I produced an irreducible representation for G bar, which is faithful. Center is trivial follows by Schur's lemma. If I had something in the center, then because W is irreducible, it will act by scalar multiplication on W. And that will tell me that, so W is after all direct sum of these guys now. And that will tell me that it has to map, for example, E0 to E0. And it acts on E0 by rotation. So G restricted to E0 is a rotation. So determinant 1 and etc. will, because of dimension of E0 is 9 and the determinant should be 1, that will tell me that the scalar, some argument is needed. I'm putting it under the carpet. The scalar is trivial because of that. You have these three things available to you. You have to use all of them actually. I think you may need to use this and this together to prove that the scalar must be trivial. Or maybe it is already visible. I don't know. I'm not seeing why did I get alpha to be 1. I just wrote this is a rotation. So why can't it be root of unity? It's a scalar homotheity on all of W. Yeah, I don't know. It should be trivial to see. I'm missing the thing right now. So in any case, you get the any central element is trivial by some basic argument. Just check that.
Do we have that rotation has to be orthogonal?
Yes.
So G bar transpose, which is
orthogonal. So orthogonal group has only two scalars in the center. Yeah, you're right. So either +1 or -1. It can't be -1 because determinant will be -1 then because it is 9-dimensional. Yeah. So correct. So the scalar has to be 1. Thanks. Correct, no, Shripad?
Yes.
Yeah, because the center, I mean, it is belonging to the center and of the rotation group also because it's central in the whole thing.
Yes.
So etc. will tell you alpha has to be 1.
Yes.
Therefore, the group is semi-simple, and because the center is trivial, you can write it as G1 cross G2 cross GR, where GIs are simple. And GI centralizes GA for I not equal to J, and GI intersects the product of the rest in trivial. So all this is standard. Now, here is the trick. So let's denote by pi I the ith projection of G bar onto GI. Now, we know there is a subgroup here. G bar U is a subgroup here. So at least one of the projections of applied to G bar U must be non-trivial. So let's say the first projection without any loss of generality, we can assume the first projection, for example, applied to G bar U is non-trivial. It can't be trivial for all the projections. So one of them is non-zero. So let's assume the first one. Now the center of, so we know G bar U is simple. So that tells me that image has to be 36 dimensional. Dimension of G bar U is 36, and when you see the image, it will, the kernel of pi1 can be at most finite. So that will tell me that GU and these are both, G bar U and this group are isogenous. So the dimensions are same. So the dimension of the image is 36. Okay? Is that okay? So now, therefore, so projection of the first factor is giving me projection of a sub of the first factor is 36 dimension, tells me the dimension of G1 is at least 36. Okay. And remember, this was the assumption here that projection at G bar U is non-trivial. So if this was valid for any other factor, then that factor also will give. So using this argument, it follows that for other than 1, all other projections must be trivial applied to G bar U. Because the moment the projection is non-trivial, that will be 36 dimensional, and then the corresponding factor above has to be at least 36 dimension, but the total dimension is 52. So that cannot happen therefore. So all other projections applied to G bar U must be trivial. Okay. Therefore, that shows that G bar U must be contained in G1. That's it, fully contained in G1. Now we know also that Gi centralize all I not equal to 1, Gi centralize G1. In particular, they will also centralize G bar U. And now it's a simple thing to see. If I take any normalizer of G bar U, say small g, that means what? G bar U, G inverse is G bar U. When you apply, so that shows that the group G bar U also fixes the idempotent GU, which is also primitive. So because this is G bar U, G inverse, so that will fix GU also, whereas it fixes U also, and there is only one primitive idempotent it is allowed to fix. Otherwise, it will be intersection of two spin lines, which will be less in dimension. So it cannot fix two primitive idempotents. So that shows GU must be U. So any normalizer element actually fixes U. So it must belong to GU, G bar U, whatever. That shows the normalizer of G bar U is itself. Okay. I mean, very tricky argument, I must say. And normalizer is itself, in particular, says that all the centralizer elements, all these centralizers. So GI centralize I not equal to 1, centralize GU. So they all must be contained in GU because of this equation. So all GIs I bigger than 1 are contained in GU, which is itself contained in G1. So that shows that R must be 1 and G bar is simple. So we have shown all of them are contained in G1 itself. So that therefore there's no other factors there. And now the last bit is the type. So to show that it is type F4, this follows by the fact, which is very interesting, that any classical simple group has dimension of the form m into n minus 1 or m into n minus 1 by 2 for some suitable integer m. And 52 cannot be written in this form. So this is funny proof, I think. So this is amazing, just coincidence, huh? 52 is not of this form. So that shows the type has to be F4. So is this okay, Shripal? Hello? Shripal?
Hi.
Yeah,
Yes, yes.
am I audible?
Yeah, you
Yes,
are
yes.
audible. I was wondering about 1 into 53, meaning just a stupid argument. You said
1 into?
m into n minus 1.
Yeah. No, so
Okay.
this is the thing is when you, what I am saying is any classical group, so there what, A and B and C and DN type, so that you will see that, see, DN and BN are done, okay, they are of this type, right?
Correct.
And then AN is
Yeah. Meaning we look for N, BN, C, and DN, and then it is clear.
yeah. So then it follows from there exactly. So that is why the type has to be F4. It's very strange. So
Yeah, so here we don't have to compute maximal torus or any such thing.
yeah. So this is, we got away cheaply here, but this argument was rather tricky. Yeah,
Yes,
I
yes.
found this very interesting. This argument is very nice. Similar. So we did it in detail here. So when I come to E6, I will run away there without giving details. So corollary is that if I take any Albert algebra now, possibly division algebra, so I'm not assuming reduced or anything, and then take the full automorphism group, then it's a simple group of type F4 defined over K. So as Pralay had asked, this of course requires a proof defined over K and so on. And any such group arises this way. So the first line is clear by base changing to some suitable extension where the algebra acquires zero divisor, I mean. So by definition, there is an extension over which A becomes isomorphic to H3C gamma, right? So we go over that extension and use the theorem. So you see that the automorphism group therefore is a twisted form of F4. So that settles the first line. And the second line is similar to what I had sketched for G2, that to say any group arises this way has to use the fact that F4 is adjoint group and isomorphic to its own automorphism group, and then use the Galois cohomology argument. So that is the proof that any group of type F4 arises this way. So this is so far this much is what I had planned for F4 for today. So I would be happy to take questions. No questions?
Yeah, my comment was really stupid, I think. 1 into
No,
50.
don't.
I heard M and N separate, and so I was
Which one?
confused. I was not
Here.
looking at slides then. But I have one small doubt. Could you please go over the proof of simplicity again?
Oh yes, simplicity was
Yeah,
yeah.
so what? Yeah, could you please briefly
Yes.
do this again?
Yeah. So first is that center is trivial. So that should imply with some work that G can be written as a direct product of simple groups.
Right.
Okay.
Yes.
And all this one can achieve.
So the dimension, so you dimension G1 has to be bigger equal 36. There, up to that, it is okay.
Yeah. So suppose now any other projection. So this was under the assumption that the projection applied to G bar U is non-trivial. The first projection, right?
Correct.
If any other projection gives you non-trivial image, then that particular factor will also be at least 36 dimensional.
Yes.
So that cannot happen.
Correct.
Because total is 52.
Yes.
So therefore, all other higher projections are trivial applied to G bar U.
Okay.
And that means G bar U has to be contained in G1.
Yes.
Okay. Now, all other GIs centralize G1, therefore G bar U. And by this argument, you prove that normalizer of G bar U is itself. Because this is the only idempotent it can fix. G bar U cannot fix any other primitive idempotent because primitive idempotent is spin group of something, and that will be a different one. I mean, a different idempotent will tell you that spin group is a different group than this. Some argument is needed, but that is the argument that it has to be itself. The GU is a primitive idempotent, and it has to be itself. It cannot be different from U.
Okay.
So once you have that, then you are done.
Yeah.
So then all the centralizers have to be contained in GU and so on. So here, yeah, you have to do some little bit of argument here why it cannot be any other idempotent.
Yes. Yeah. Thank you.
Yeah. So I better not venture into it, but you can argue it out. It's not very difficult, I think. That part is not difficult.
Could you do it in the tutorial maybe?
Yes, we just remind me. I will fix this in the tutorial, definitely.
Okay, great.
But other than that, once you have that, then you are done, right?
Yes, then it is clear.
Yeah. So that I will fix in the tutorial. Okay. So this was the case of F4. Now, if you are alive, I will go to the next one with some courage, of course, required from your side, but not very complicated. Now, I'm going to be little sketchy here. So let's fix any Albert algebra over K, and let so H lower bar denote the group of linear operators from AK to AK that leave the cubic form invariant or fixed, whatever. And that corresponds, the cubic form corresponds to a trilinear form. Remember, I have removed characteristic 2 and 3, so I can trilinearize that in a way that xxx coincides with determinant of x for all x. Now, one can define a cross product. Sometimes this is called Freudenthal cross product because I think Freudenthal came up with this. A cross product on A can be defined, which is bilinear, by this equation. So this form is non-degenerate. So one can define this. X cross Y is defined by the fact that bilinear product with Z, the trace bilinear form with Z gives me 3 times the trilinear form XYZ. So this pins it down. This is the definition for X cross Y, and that gives me X cross X applied to, if I put Y equal to Z equal to X, then I get X cross X. X is 3 times XXX, so 3 times determinant X. So there's some confusion here. Huh? I wanted to say that X times X cross X is determinant X. Is that clear? Anyway, whatever. So this is what I want. Finally, X times X cross X should be determinant. It should, maybe I made a mistake here. Huh? Just I'm getting a little confused. X cross, yeah, there's 3 coming here. So it will be 3 times determinant X according to this, right? I don't know. Some scalar factor is causing me confusion here. But this is finally what I want. X times, so usual 3 by 3 matrices, you have the notion of adjoint, right? Which is really, when you write down the Cayley-Hamilton equation, you take the determinant on the right hand side and factorize the matrix out. So you get something like, so if capital X is the matrix, then it is x cube minus trace x times x square plus some expression times x minus determinant x is 0. So let's take determinant on the other side, and from the left hand side factorize x out. So what remains inside is a quadratic expression that is x cross x. And the similar thing can be defined for these Hermitian matrices or Albert algebras in general. One can define this.
So Manish, I'm a little confused.
Yeah.
So you said x times x cross x. It shouldn't be inner product.
Pralay, I can't hear you properly.
No, I mean you are writing
No, this is
x
x
cross
times.
y.
It is not inner product. It is x times x cross x.
But you are deducing from the identity above.
Yeah. This is non-trivial. This has to be proved. So, but the definition of x cross x is from here.
Definition of x cross x involves that.
Yeah. So I'm giving a sort of sketchy proof which requires some thinking. Is you write down the Cayley-Hamilton equation for x, okay, and take the determinant part on the right hand side. So what remains on the left hand side is will look like x cube minus trace x times x plus some coefficient times x equal to determinant x. So that all from the left hand side you remove x common. So what remains in the bracket is a quadratic expression in x, and that is really x cross x. One can explicitly write down what is x cross x. So I am not spending too much time here, but I told you roughly what x cross x is, right? You just take Cayley-Hamilton equation, take the determinant on the other side, and from the left hand side you take x out, and inside you will have a quadratic polynomial in x, that is your x cross x. Okay, so now using this trace bilinear form, which is non-degenerate, we can define what is sometimes called contra gradient, or I am calling it transpose inverse, for any linear map from A to A. Let's denote it by T star. So what is the definition of T star? Is Tx bracket with T star y is bracket of xy. So it is like transpose inverse. So because this form is non-degenerate, one can do this. Any non-degenerate bilinear form has this property. You can define the transpose inverse for any linear transformation, right? And the property is T star star will be T, ST star will be S star T star. So these are all trivial things. We know these things. Then the proposition is important. It says that if I take a reduced Albert algebra, that means something also from H3C gamma, and I look at the group of all invertible endomorphisms of A which preserve the determinant. Okay, so when you apply the transformation and take the determinant, that is same as determinant of the original matrix. For that should happen with all matrices. So collect such transformations, and that group is called H lower bar. Then this is a criterion when an element of GLA belongs to H lower bar. So this is if and only if Tx cross Ty, so cross in that sense I defined, equals T star of X cross Y. And this map T goes to T star is an outer automorphism of this group of order 2. So this proposition has been done for the base field, but this holds for any extension of K. So really this proposition is for the algebraic group H lower bar. So there we have explicitly written down an outer automorphism of H of order 2. So this fact will be useful later. So we will recall this later. Now, one more fact here, which I am not proving, is that the polynomial function determinant, this cubic form, is actually irreducible polynomial. So now comes the irreducible variety again that we need for E6, namely look at the determinant 1 elements of AK. So over the algebraic closure, everything is a sort of 3 by 3 matrix. So I can talk of determinant of x equal to 1. So collect all such guys. That is an irreducible variety. And the dimension is 26 because, why is the dimension 26? So this is 27 dimensional space, and then I'm cutting down the dimension by 1. So it's a 26 dimensional irreducible variety defined over the base field. Next one is about orbits, describing the orbits of H in A, but for reduced Albert algebras. So if A is a reduced Albert algebra and A and B are two elements which have same determinant, non-zero determinant, then I can connect one to the other by an element of H if and only if I look at the non-degenerate bilinear forms A and B define. What is the definition of the non-degenerate bilinear form? At x and y, the value is determinant A inverse, the trilinear form XYA. So these two bilinear forms are equivalent if and only if you can find an element mapping one to the other. So these are very non-trivial facts, and I'm not going to do the details, but just curiosity sake, it's important for us later on in calculation. Basically, over an algebraically closed field, any two symmetric bilinear forms in the same dimension, which are non-degenerate, are equivalent. That will tell us that the group acts transitively there. So that's the reason for this sort of result. So we will use this. Stabilizer of this action of H at the identity element. This is a theorem due to McCrimmon and Jacobson that any isometry of the determinant which fixes the identity element is actually an automorphism. So this is precisely the stabilizer at identity. See, this is very different from the octonian case. There, this was not at all true. But here, indeed, it is maybe because we have more space to maneuver here, that anything that fixes identity and belongs to H is actually an automorphism. So we have the stabilizer, we have the transitive action. We will see why it is transitive. We almost did that. So the theorem is that the group of isometries of the determinant is connected, simply connected algebraic group of type E6 defined over K. And this is yet another beautiful theorem. So the dimension of AK is of course 27. And as I said, any two non-degenerate bilinear symmetric forms of the same dimension are equivalent. That implies H bar acts transitively on the norm 1 elements because of this. So here I have a determinant of two elements is both equal to 1, and these two bilinear forms will be equivalent because the field is algebraically closed. Therefore, I can find an element, an isometry of the determinant mapping A to B. So this group acts transitively on norm 1, variety of norm 1 elements. This is non-trivial actually. And then stabilizer is the automorphism group, which is 52 dimensional. That tells me the dimension of V on one hand is 26, on the other hand it is dimension H bar minus 52. So that gives us dimension of H bar as 78. And connectedness follows because irreducible. Okay, so sorry, what am I trying to do here? So on AK, this group, this vector space, G bar action on AK, we have studied this already. The only invariant subspaces are the scalar multiplication, scalars, and the trace zero elements. And H bar leaves neither of these invariant. So this follows by, of course, if it left this invariant, that would mean every norm isometry is a scalar multiplication. That's not true. I mean, there are so many automorphisms, for example. Similarly, here also one can produce explicit isometries which do not satisfy this. So this leaves neither of these subspaces invariant. So that's really an exercise. Maybe in the tutorial I can sketch this, how to do this, by writing down some explicit elements. So you know what I'm saying is, the claim here is, first of all, we have already shown that the automorphism group leaves any invariant subspace of AK under the automorphism group has to be either this or this. That much is something we saw. Next statement is H bar leaves neither of these invariant. And to see that, we have to produce explicitly some elements which violate preserving this and this separately. So we will hopefully I will remember to do this next time. So this shows therefore it's an irreducible representation for H bar, because if you took an invariant subspace, what did I do? Oh my god. Yeah. How did I go so much backwards, huh? Yeah. What I am saying is, if I had an invariant subspace for H bar, say contained in this, I am trying to prove AK is irreducible for H bar. Because if there was an invariant subspace for H bar, that must be invariant for G bar also, because G bar is a subgroup here. And the only invariants for G bar is KE and E per. However, we know there are elements here which do not stabilize this or this. So that will show that AK is irreducible for H bar and faithful, of course, trivially faithful. So by our funny lemma, H bar is reductive. And Schur's lemma, so I want to prove center is mu3 with the group of cube roots of unity. By Schur's lemma, anything is a scalar multiple here, scalar multiplication here. And yeah, so why is it mu3? Because, yeah, let's go back here. Uh, 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 uh. What did I do? Yeah. Right. Yeah. So, so if you take a central element, then it centralizes F4 for the automorphism group, for example, right? So once it centralizes the automorphism group, we know the automorphism group fixes this pointwise. So the stabilizer, that centralizing element must map this to itself. That's where you see that it's a, first of all, it's a scalar multiplication and it maps this to itself. No, I'm not getting this argument. What is going on? I wanted to say it's in mu3. Yeah, I'm sorry about this.
Preserves the determinant, right?
Yeah, determinant where? I'm sorry, I'm confused now. It is the determinant exactly, but where is the three-dimensional space? I'm looking for one. I'm not finding
So
it.
determinant is cubic on k times c.
Ah,
Right?
yeah, yes, yes. It's a cubic form and it's a scalar multiplication. No. Scalar multiplication and no. Can you repeat?
So it takes e to a times e, let's say.
Correct.
So if you take the determinant, aren't you getting a cube equals 1 or am I?
Yes, you're right. Yes, that's what. Yeah, that's all. Yeah. So take the determinant, then it's a cubic form, so cube will come out. Indeed. So you get scale that scalar, whatever the scalar is, its cube should be 1. So and it's a non-trivial. I mean, we are trying to prove the centralizing element is mu3. So the center is contained in mu3, and any cube root of unity gives you a centralizing element because cube root of unity. So you multiply anything by that cube root of unity, then the norm is preserved. That shows that actually center is full mu3. Okay, so I hope this is okay. Everyone, okay, Shripal? So, let me repeat here. So, first of all, it's a faithful representation, irreducible. If I had a central element, then Schur's lemma says it must be a scalar multiplication on this algebra. And then take an element, it maps, scalar multiplication maps this multiples of e to themselves, and that tells me by taking the cubic form applied to that the scalar cube must be 1. So it's a cube root of unity, and conversely any cube root of unity gives you an isometry by scalar multiplication. So the center is full, and that shows it is not just semi-simple, it's also simply connected. Because no, I have not shown the type yet. Let me go slow. So H bar is semi-simple from here, and by an argument, what we saw for F4, similar argument as that, a little modification is needed because the center is no more trivial here. But similar argument, I am saying, one can show that H bar is simple. For example, by going modulo the center. So you go modulo this finite center, you kill the center and then use that kind of argument to write it as product and so on, and use projections, restrict the projections to F4, for example, and so on. So similar argument tells you H bar is simple. And then, so we have the dimension here 78, and then we have simplicity that reduces already the possible types to B6, C6 or E6. This is amazing. Actually, their dimensions are all 78. Interestingly, they can't be more than that. So, and then we know that H bar has an outer automorphism of order 2. We explicitly exhibited one that throws away these two possibilities. So it pins down the type to E6. And the center is full, therefore this is simply connected. I think this is quite very, I don't know what to say, but it looks very coincidental, all this, but it's an amazing thing. Huh? It pins down everything. So any questions?
So why was it an outer automorphism?
That needs a bit of checking. I haven't done that, but it's an outer automorphism.
It acts non-trivially on the center.
Yeah, one has to show that it acts on the Dynkin diagram. Actually, it's a Dynkin diagram automorphism has to be proved. I have not done that proof. Yeah, so that will show that it's an outer automorphism. And then just a little bit noise on any questions?
Oh, 1 second. Yeah.
Yes.
So how does the simply connectedness follow?
Because the center is full. This is the full possible center for E6 type.
How do we know that?
No, that is root system calculations. Root lattice, weight lattice, modulo
Right.
root lattice.
And the ratio being 3.
Yeah, that will be order 3. And we already have full account here, so it must be simply connected.
Okay.
So can one also use that to rule out B6 and C6? The center.
I did not check that. Well, yeah,
Yeah,
maybe.
the center should be enough, right?
Yeah, center should be enough. Yeah, you can rule that out indeed, because this is order 2. No, B6. No, so order 2 center here, right? No, sorry, 6. 6 is
So 13. So 13 doesn't have center.
13 doesn't have. Yeah, 13 doesn't have.
Just order 2 center, right, for spin 13.
Yeah. Spin 13, right? Yeah. Yeah, that should work. Yeah. Okay. So E7, I'm not, as you saw, I'm decreasing in my details. So E7, the least detail I have given so far, which is as follows. So you start with an Albert algebra, which remember is a twisted form for the reduced or split Albert algebra. And you construct these weird matrices where the diagonals are from the field, and off diagonal you put elements here. There is a product here which I am not going into, but I just come to the point straight away. This dimension is 56, as you can see. And this will be an irreducible representation for this E7 I am describing. On this, we have a quartic form. So degree 4 homogeneous form, which is homogeneous polynomial, which is defined with these parameters. X and Y are from A, alpha and beta are from K. And this hash means X cross X, and everything else is defined. It is a degree 4 polynomial as written down here in 56 variables. And the theorem is that the connected component of, so this doesn't give you connected group, the whole isometric group, but the connected component of identity of the isometric group of F in GL of M is simply connected of type E7 defined over K. So, this is still preferable because this dimension is 56, and the Lie algebra of this is E7 is, I guess, 133 or something, right? So it's much bigger. So this is preferable. This form is quite preferable. I have not given references today, but in the next lecture I will. Okay, let me end with a remark here. So this is a simply connected of type E7 defined over K. The remark is that in the above, if we take A to be split in both the cases, E6 or E7, then we get split simply connected forms of E6 and E7, which are defined over K. So, of course, I have not given any proofs of these things. This is a paper of Springer. These details you can find either in the paper or even Springer's second or whatever latest edition of his algebraic groups book in the end, he makes a remark about this form of E7. Yeah, so today, this is all I have. Next lecture, I plan to make some little bit noises about what do I want to say? I want to say all possible ways one can construct. So one can construct Albert algebras, all of them actually. So though their classification is still not known, but one can give explicitly all constructions. So all forms of F4 can be written down. E6 and E7, certain types of forms can be written down. So my plan is I will talk about E8 little bit, and then come to classification of isotropic groups in terms of Tits indices. Then maybe end with Tits Freudenthal magic square, which gives you some forms of exceptional Lie algebras. And from there, one can construct algebraic groups by taking the connected component of automorphism groups. Yeah, so this is today's lecture. Any questions are welcome.
I was aren't there multiple forms of E6 which can contain the same F4?
Yes.
If one of them is defined using this Albert algebra, the other guy cannot, or
No, but I must say I am very ignorant about more forms of E6. So the only versions of E6 I know, all of them are coming from construction of Albert algebras. So somewhere or the other, one will have an embedding coming from embedding of related F4 in that particular form. So
so you're saying it? Sorry.
No, one can. I'm sure there must be some other forms of E6 possible, which I have not worked with, so I cannot negate your question immediately.
No,
So what I'm saying is the only versions I have dealt with are related in one way or the other to Albert algebras, and there one can see some embedding of F4. I have to check if one. So for example, yeah. So you can do the following. So you can take an isotropic E6. Let's say the anisotropic kernel is some classical group, right? So you will have a construction of that kind of E6 starting from a classical group actually, and so the relative root system one should figure out whatever it is, and perhaps that will not have an F4 embedding. I don't know. I'm just guessing. I should check. I have not thought about this. I should check this. Yeah.
Thank you.
But do you agree there is a possibility of that? So you understood what I'm saying, right?
Yeah.
So you take a form of E6, which is isotropic, and its anisotropic kernel is a classical group, and the relative root system is also, let's say, classical. So both perhaps are possible. I will check. I should. I don't remember by heart, but it should be possible.
Thank you.
Yeah.
Manish, will you also talk about the magic square in the next lecture?
Oh, I plan to do that because it's just I'm not going to do some proofs there because proving the magic square means pinning down the root systems and so on. That is not possible now. So
Yes.
I will just draw the magic square and explain how to read it and what it gives, and say the magic about it. In the sense, it is something like periodic table. Some forms were predicted using the symmetry in the diagram. So, and then they actually found those forms. So it's something like that is perhaps the magic there. I don't know any other.
Yeah.
Personally, I dislike the word magic in mathematics, but there is so much magic actually. So magic means something not understood to me. Yeah. So any questions or remarks or suggestions for what to do next is welcome. So I can unshare this, Shripad, or let it be.
Yes, I don't think people have any questions.
So I just cancel these files, right? Then or minimize it. Yeah,
Minimize, and you have to
Yeah.
say stop presenting.
Correct. Stop presenting. Yeah, good. I can see, but all are only icons. I don't see people. I think the number of audience is fast converging to a low number.
I will stop the recording now.
Sure.